Let's see. Screen number 2. Let me know when you can see my screen. Everything good?
Yep.
Okay. So let me move this dock to this monitor. Okay, so here we go. Hello, everyone. My name is Yayun. Thanks for joining this meetup tonight. I know that people are usually feel very tired at this time after work in the middle of the week, especially for audience from East Coast, and the local time is already close to the bedtime. So I will try to make this talk not as boring as the name sounds like. A little bit about myself. I am a data scientist at Microsoft. Before joining Microsoft, I obtained my PhD in industrial engineering and operations research from North Carolina State University. I also put my LinkedIn here, so feel free to connect with me on LinkedIn. My talk today is about reinforcement learning. This talk is ideal for data enthusiasts who do not have any prior knowledge in reinforcement learning. So let's move to the next slides. Let me turn on the laser pointer so it's easy for you to see. So in my opinion, a good intro-level talk should contain more intuitive and less mathematical knowledge, which is easy to understand for most enthusiasts or data enthusiasts. Also, I will cover more topics without going deep into every topic. Hopefully, you will find this talk to be fun, so you won't leave until the end. Also, now it's the end of our day, so I bet most of you have already been tired. So I will try to explain all the concepts as clear as possible. Please feel free to stop me and ask questions anytime. Also, I think most of us may not really use reinforcement learning in our daily work. So it's not necessary for us to go too deep. Actually, for myself, I never use reinforcement learning in my work, but I gained interest in that when I was doing my PhD. And I used some reinforcement learning algorithms in my PhD dissertation as well. Hopefully, at the end of this talk, you are able to understand what reinforcement learning is and also mention some example next time when people around you are talking about reinforcement learning. Actually, that's my first tech talk after graduation, like I mentioned earlier. And I'm also learning how to be a good presenter. So all the comments or thoughts are welcome after the talk. Also, feel free to connect me on LinkedIn again. So comes to our topic today. When we mention reinforcement learning, there are great applications so far that we need to know. Many of you may already hear about AlphaGo. It's a computer program created by deep learning, and it can created by DeepMind, this company. Now it's acquired by Google, and it can play very well and even defeat the Go world champions. In March 2016, AlphaGo defeated Lee Sedol, who is the strongest player of the last decade with an incredible 18 world titles. This match was watched by around 200 million viewers. The second example that I'm giving here is self-driving cars. Some of the autonomous driving tasks where reinforcement learning could be applied, including trajectory optimization, motion planning, dynamic pathing, controller optimization, and scenario-based learning policies for highways. For example, Wave, which is WAYVE, that company, is building a full driving software system to train the car to drive in a complex, never seen before urban environment, which is very cool, actually. You can look it up more if you are interested. The third example is an AI-powered recommendation system that is used to improve the energy efficiency of Google's data center. The impact here is huge. Even minor improvements could provide significant energy savings and reduce carbon dioxide emissions to help combat climate change. Reinforcement learning also have applications like in finance, for example, helping make decisions on whether to hold buy or sell a stock, and also like in healthcare, like for example, automated medical diagnostic. So actually, there are already lots of existing applications and ongoing research in reinforcement learning. Okay, so let's go to the next slide. Oh yeah, before going deep into reinforcement learning, let's look at how it fits the machine learning field. You must already hear a lot about supervised learning and unsupervised learning, which are two main ways where we could train our models depending on the type of data we're providing with. So actually in supervised learning, we are provided with a set of inputs and outputs. So our data are already labeled and we know the ground truth behind them. It means that once your algorithm is trained on the train set and has made predictions on the test set, you can have immediate feedback of its performance since we already know the real output. In unsupervised learning, we are provided with data which are not labeled or categorized. The goal of the unsupervised algorithm is inferring the inner structure of those data, finding common patterns, and trying to cluster them into categories. So far, so good. So, however, what happens if we are not provided with any data at all, and we want our algorithm to learn from the surrounding environment? And this is where we can see the magic of reinforcement learning. If you think about many automated systems like self-driving cars and robotics, you can see that those machines, like for example, cars and robots, they are not provided with any historical data. They have to collect them while working. So the idea is that those machines have to approach their task through several attempts, learning from their mistakes, for example, crashing against a wall, and avoiding them in the next attempt. So reinforcement learning is one of the basic subfields within machine learning. In a reinforcement learning framework, an agent interacts with an environment to learn what actions it needs to take in any given environment state to maximize its long-term reward. So let's explain this concept a little bit more by considering this example, which refers to Markov decision process. Maybe it's your first time to hear about the Markov decision process, but I will repeat this term a lot later in our talk, so you will get used to that. The idea is that we have an agent, which is a robot in this example, and we have an environment, which is a labyrinth. The agent has a personal representation of the environment, which is called state. Then it needs to interact with the environment. And the way it does that is through action. After each action, the agent will have a new state of the environment, as well as the feedback on its action in terms of reward or penalty. So to make it easier, imagine you are visiting an apartment for the first time and suddenly the environment gets dark and you cannot see anything. You want to reach the door, but you don't know the way. How would you behave? So you will probably start by walking very slowly and randomly, having in mind a certain representation of the apartment, which is a state. And then you bump into a wall on the right. Now you can mentally update the state of the environment. And at the same time, you are receiving the negative feedback on your action, which is a penalty. Now you learn that the action you did was not correct. Hence, you will proceed towards another direction, and surprisingly, you reach the door. Now you will receive positive feedback, which is reward on your action, since you reached the goal. So the same would happen for this little robot, this agent here, trying to cross the labyrinth, which is the environment, and reach the prize, which is a goal of its task. So you can see if this robot follow this red line, then it receives a penalty, -1. And if it follows the green line, then it reaches to the door and gets a reward. So the idea of a reinforcement learning algorithm is finding a set of actions, which is so-called policy, so that the present or the discounted value of rewards is maximized. Okay, so from the robot example, let's get a quick summary here. In a general situation, the agent here takes an action, observes the state of the environment, and gets a reward based on the current state of the environment. The goal is to maximize the long-term reward that the agent receives as a result of its actions. Reinforcement learning is well suited for solving problems where an agent can make autonomous decisions. Our focus today is reinforcement learning based on models called decision process, Markov decision processes. So instead of just throwing the definition of Markov decision process to you, I will start from the basic and extend it to the concept of MDP. So we're going to start from Markov property, and then we're going to introduce Markov process based on Markov property. And later on, we're going to talk about Markov reward process. And the last, we're going to have Markov decision process. So now let's see what Markov property is. So Markov property can be interpreted that the future is independent of the past given the present. So a state, so like now we are at time t, and we are in this state as with the subscript t. What will happen in the next time step t plus 1 is only dependent on the current state as t, rather than the whole history. So you can see that actually that's a conditional function. So like there's a vertical bar here, and there's a vertical bar here, like before the vertical bar. So that's the probability we want to get. And after the vertical bar, so that's the condition. So you can see like we can just throw away the condition of the history, and we only care about like the current state, because the current state will decide like what's gonna happen next, rather than like the whole history. So based on this concept, and now we can have like a probability like this way. So this P, this probability from the state S to the next state S prime is the transition probability. It is defined as this way. And now we have transition probability, and we can also define a transition probability matrix. So like each row represents the possibility of current state, and each column is the possibility of next state, and each row of the matrix sums to 1. It may seem a little bit confusing here, but later on I'm gonna introduce an example, and you can understand like why we introduce like a transition matrix like that, and why like each row of the matrix sums to 1. So based on the Markov property, now we have a Markov process, which is a memoryless random process. We can also interpret it as a sequence of random states, S1, S2, with the Markov property. So we have two parameters to define the Markov process, the capital S and the capital T. So the capital letter S is a finite set of states, and the P is the state transition probability matrix we showed like in the last slide. So let's look at this example to help you better understand what Markov process is. So like in this example, if a student needs to pass a course, he needs to go through class 1, class 2, class 3, and then pass. And there are several distractions here, including Facebook and Sleep and Pub. So like in this case, we have 1, 2, 3, 4, 5, 3, we have 7 states, including like class 1, class 2, class 3, pass, and also 3, like Facebook, Sleep, and Pub. So like in this example, like we have like, so those circles are the states in this example, and those probabilities here, like for example, if we are in class 1 and we can go to Facebook with a probability 0.5, or go to the next class with a probability 0.5. So those probabilities are called transition probabilities. So actually from those like transition probabilities, we can have a transition probability matrix. So how this matrix is created, so we can see from here. Like just like I mentioned, from class 1, we go to Facebook, we go to class, and then you can see that it also show this in this matrix. So C1 means class 1, and we go to class 2 with a probability 0.5, go to Facebook with a probability 0.5. And when we are in class 2, we can go to sleep with a probability 0.2. So this is 0.2. Or we can go to the next class with the probability 0.8. So you can see from here and to here, that's 0.8. So you can see like each row sums to 1 in this transition probability matrix. Okay, so now we have defined the Markov chain or the Markov process. We have like a set of states and we have the transition probability matrix. Let's check out some sample episodes in this example. An episode in a Markov chain problem is a sequence of states that ends in a terminal state, or we call it absorbing state. So in this example, we can see sleep is a terminal state, because once we get to the sleep state, there's no way to get out since there's no arc that goes outward. There's only like arcs that going inward to the sleep state. There are multiple episodes in an MDP problem. Like for example here, if we start from like the class 1, which means our first state is class 1, and we can, like for the first episode, C1, C2, C3 pass sleep, which means we follow this episode. From class 1, go to class 2, go to class 3, and then we pass, and then we can go to sleep. That's perfect. Let's look at the second episode. It's C1, so we start from class 1, then go to Facebook, and then we stay here one more time and go back to class 1 and go to class 2 and go to sleep. So we didn't finish this, like the course, but we still go to sleep eventually, which is okay. So let's look at the third episode. We start from class 1, go to class 2, go to class 3, and then we go to the pub. And we go back to class 3 because, like we forgot what's going on in class 2. So because like we may drink a little bit more in the pub. So that's why we go back to class 2 and go to class 3 and then we pass, then we go to sleep. So there are some distractions on the way, but finally we still pass. So we can interpret this fourth episode as well. So actually for most MDP problems, there are like multiple episodes, like just like multiple like scenarios in MDP problem. So let's move to, we have talked about Markov property and Markov chain. So now let's talk about Markov reward process. A Markov reward process is a Markov chain with values. So you can see from the definition, now we have 2 more parameters compared to the definition of Markov process. So the R is the reward function and the gamma is a discount factor. You will see later like why we introduce a discount factor here, but briefly, it's the present value of future rewards. When gamma close to 0 leads to myopic or nearsighted evaluation, it only cares about like the first reward. When gamma close to 1, it leads to far-sighted evaluation. It cares about like all future rewards. We're gonna explain more like later on. But you can see like here we have 2 additional parameters and we have like a reward functions here. And yeah, let's look at the same example, but now you can see like for each state, we have like a reward here, like which means if we are in class 1, we have like this reward. When we are in Facebook, we have this reward. So So before going to the definition of Markov decision process, we need to introduce two terms, two definitions here. So the first definition is called return. So return, like G, the capital letter G with the subscript T, is the total discounted reward from time step. So that's actually from time step to the end of this current episode. So you can see for this term, there is no gamma attached to that. But starting from the second term, there will be gamma attached to that. So which means actually the first term is our immediate reward from current state, and we don't have discount factor. But in the next step, we're going to multiply the reward by gamma, which values immediate reward above delayed reward. So let's think about from this way. If the reward is financial, we can interpret it as immediate rewards may earn more interest than delayed rewards. And also it's a reflection of animal and human behavior, since we prefer immediate reward. For example, if we can have a candy today, we may not want to wait until 10 days later to get 5 candies. So people prefer to make the choices for now and to get the rewards immediately. Another important reason why we put a discount factor here in this Markov reward process is that it turns out to be mathematically convenient to discount rewards. Here we guarantee that the algorithm will converge and avoid infinite returns in a loopy Markov process. So it may sound complicated, but remember in the example we just see, actually there is a terminal state sleep, and when we reach to that state, that's the end. However, it's possible that in some states it's just keep looping itself. So there's actually no end of the state. It will just continue. The whole episode just continue forever. However, if we have a gamma factor here, so the more time we are in this episode, the more rewards we're gonna get. So if the gamma is between 0 and 1, then this whole function will converge eventually. But if this gamma is 1 or above 1, it is possible that it may not converge. Actually, I skip all the convergence proof or optimization proof here to not overwhelm you with too much math. However, if you are interested to learn why the whole thing is set up this way, feel free to start from here and read more materials afterwards. And the second term that we need to introduce is called the value function. So the state value function of an MRP is the expected return starting from state S. So you can see that's the expectation of all the returns. So we take into consideration of all the possible episodes, and we do the average here. So you can see on the left side, the state value function is only a function of state rather than the time step t. But on the left side, you can see the return is a function of time. So let's move to the, finally we can move to the Markov decision process here. A Markov decision process is a Markov reward process with decisions. So it's an environment in which all states are Markov. So we have an additional parameter in this definition, A, which is a set of actions. Since we introduce a set of actions, our transition probability and reward function also change a little bit. You can see the small change here. So, it's now example time. So you can see now we move all the the state's name to the arcs. So each arc represents an action. So moving from here to here, we take this action, Facebook. And moving from here to here, we take the action, quit. So that's how the MDP problem is formulated, which means all the arcs represent actions. So before we going into another specific example, let's look at some other definitions here. Policy. So policy is a distribution over actions given states. So it provides us the probabilities of the actions when the agent is in state S. So you can see like it only depends on the current state rather than the time. So policies are stationary, which means time independent. And by introducing pi, we can now connect Markov process, Markov reward process, and Markov decision process together. So given an Markov decision process with those bunch of parameters and the policy pi, the state sequence S1, S2, and so on is a Markov process with those two parameters. The state and reward sequence S1, R2, S2, R3, and so on. It's a Markov reward process with these parameters. And actually, like you can like derive like those functions, equations on your own if you are interested in that. Actually, like they look complicated, but they are actually pretty straightforward once you look into them carefully. You can verify these equations on your own if you want to, but I will not go through, like, I will not go into explaining like the details here. So we have another two new definitions here. The first one is the state value function of an MDP, which is the expected return starting from state S and then following policy pi. So you can see like there is that's the return we defined in the previous slides. And the second definition is the action value function, which is expected return starting from state S, taking action A, and then following policy pi. So if we compare like these two functions, you can see that this is the state value function, and this is the action value function. So this one have that action parameter here, but this one doesn't. I'm gonna show you like how we interpret this like state value function and action value function later on. So, okay, just a little bit more math here. So since we defined like these two functions here, and we call that like a Markov decision process is solved when we know the optimal value. And actually the optimal value function specifies the best possible performance in the MDP. So what is the optimal functions then? So these two functions are the optimal policy, are the multiple functions that we obtained by finding an optimal policy that can make the two values like be the like largest values. Okay, finally example time. Oh, okay, great. So okay, like I think we have talked about like all the boring like equation like definitions like parts, and now we can have some like that's the last like interesting example, and then we're gonna talk about like something else. So like in this Markov decision process, like remember we talk about like the action value and the state value. So in this example, like all the numbers in the circles are optimal state values, and the numbers on the arc, which is actually the Q star here, they are the optimal action value. So I'm gonna tell you like how we interpret like this example. For example, now we are in this state, and if we go to that state, we're gonna receive the reward 5. And if we go to like this state, we're gonna receive the reward 6. So 5 and 6 represents the action value for each arc. So definitely we're gonna pick like this one since 6 is larger than 5. So we follow this route, follow this arc. And same here, like if we are in this state, and if we follow this arc, we're gonna receive reward 8. If we follow this arc, we're gonna receive reward 0. So we're gonna pick the bigger one for sure. So we're gonna follow this arc. So that's how we interpret like those values here. And also like the numbers in the circles are also correlated with each other. Like for example, from here, like we have the state value is 6. And if we go to this arc, we're gonna receive like -2, the reward, but we're gonna have like the 8 reward like eventually. So you can see like 6 equals -2 plus 8. And same thing here, like the 8, the state value equals to -2 plus 10. So actually the value of the capital letter R represents the immediate reward, while the values in the circles are the state value that we're gonna receive like in the long term. So that help us to like, I hope that this explanation help you to understand like how like the state value is and what is the like action values. Actually, those are the numbers on the arc or in the circles. However, like I just like show you those numbers like directly in this example, but we don't know like how those numbers are calculated. Actually, I'm not gonna cover how to solve like the MDP, the Markov decision process problems like directly today. Actually, it's a process of value iteration. Sorry, there's some noise here. Okay, here we go. So actually, I'm not. So actually, to solve an MDP problem, it is a process to do the value iteration, policy iteration, and to solve like some functions called Bellman functions. So actually, it's there's a bunch of like mathematical work you need to do, and you can check it out later, like after this talk, if you are interested in like how to go get those numbers by solving those like a bunch of functions. However, let's just briefly talk about like the methods we use to solve a problem like that. It's called dynamic programming. So dynamic means a sequential or temporal component to the problem. And the programming is actually not the programming, like the coding, like we usually talk about. It actually means optimizing a program or like a policy. So for dynamic programming, it's a method for solving complex problems, and it can like help break down the problem into sub-problems, and we solve the sub-problems, and then we can compare like the solutions of the sub-problems into like the final solution. So actually, like not all the problems can be solved by dynamic programming, I mean, for sure. And for the problems that can be solved by dynamic programming, there are 2 requirements. So the first requirement is like optimal substructures, which means like the problem, the optimal solutions of that problem can be decomposed into sub-problems. The second one is like we also have like overlapping sub-problems for the original problems. So the sub-problems recur many times. So that's just to give you like an idea of like what dynamic programming is. Actually, like you break down like the whole problem into like different parts and you can combine them together. So there are also like lots of Yayun is requesting to annotate. I think I can click approve or decline. Can you see my screen? I think someone is requesting to annotate the shared content. I think that's a mistake, so I will just click decline.
Yeah, go ahead.
Okay. Okay, no problem. Sorry about that. So yeah, here I just want to give you some ideas about like what dynamic programming is. Actually, it's a programming. I mean, that's a very important algorithm that not only have the applications to solve the Markov decision process, but also for some like some coding stuff. Like, so let's move to the next slides. So now, actually, we only talk about Markov decision process, which is actually for model-based reinforcement learning, which means we can formulate the problem into a Markov decision process, and we know that like all the parameters, like for example, including state transition probabilities and the expected reward from any state and any action. So we know like that's a model, and we know all the parameters for the model, and then we can formulate the problem into an MDP. However, like it's possible like sometimes the reinforcement learning problems cannot be formulated into a model-based problem. So to deal with those scenarios, we have model-free algorithms that do not require knowledge of Markov decision process, like transitions, rewards. The focus today is model-based reinforcement learning. However, I will just talk about like Monte Carlo, like this example, like briefly. So actually, Monte Carlo is one of the model-free algorithms, and it can learn directly from like the episodes of experience. Some of you may already heard of Monte Carlo. It has been used a lot in different disciplines. However, what exactly Monte Carlo is? Any method which solves a problem by generating suitable random numbers and observing that fraction of numbers obeying some properties can be defined as a Monte Carlo method. Let's do a simple example here where we will try to find out the value of pi using just a pencil and a pen, just a pencil and paper. So let's draw a square of unit length and draw a quarter circle with unit length radius. Now assume we have a hyper who is a robot, and it will put as many dots as possible on the square randomly, like for example 3,000 times, and resulting like in this following figure. Like you can see there are lots of dots here. The robot will also help us count the number of dots inside the circle, which will give us the capital letter N, which is the number of dots inside this quarter circle, and then we can get pi. So how could we get pi from here? Let's do like a simple derivation here. So we know the area of a circle equals to the pi times the square of r. So we can get pi equals to a divided by r squared. And because the quarter circle is just a quarter of a circle, so if we assume that the area of this quarter circle is the capital letter S, and then the area of like a circle is four times of the quarter, so that's 4 times S divided by r squared. And we can see like the S divided by r squared is actually like the numbers, like the number of dots inside this quarter square divided by the total number of dots like in this square. So if you want to like get like maybe more like maybe better estimation, you can increase the number of dots here. Like you can make it to be like 3, like it's 3,000. You can make it to be like 30,000 or 300,000. Then you will like get an estimation of pi even closer to the real value of pi. So Monte Carlo methods has been used a lot like in the computer simulations. So like it just like runs some computer programs and keep doing the same thing like again and again, and at the end and you're gonna summarize them together and do the average, and then you can get an estimation of the real value. So that's the idea behind Monte Carlo. So we can also use this idea to solve an MDP problem, because like in an MDP problem there are like multiple episodes. So you can just like run some programming and to have like a bunch of simulations of the episodes, and then you do the average. So you can see like in this function we have like an average here. So we'll get like expected value of those, and then this one can be our expected return of total discount reward. So that's just like some basic ideas to help you to understand like what are like some model-free algorithms can help us to solve like the reinforcement learning programs. So here we are. Actually, that's all the stuff that I want to talk about like in my talk today. So I mean, like usually like after a talk, like I try to like summarize some like takeaways that I can get from like any talk. It's gonna help us refresh the memory and to like keep it like, and we can like apply that in the future. So I'm trying to help you to give some takeaways here. So hopefully like you can like it can help you like refresh your memory as well. So the first takeaway that I want you to have is, you know, like what is reinforcement learning now, and you can compare that to supervised learning and unsupervised learning. So remember at the beginning, like supervised learning is like there's data and we have label. And in supervised learning, we have data but no label. And in reinforcement learning, we don't have data at all. So that's just like a very brief way to differentiate those algorithms. So the second takeaway is you can like talk about some examples of reinforcement learning, like for example, some games like the AlphaGo. And actually there are like lots of games that can be played by reinforcement learning. And also like the self-driving cars. So that's also another example. And the third takeaway that I want you to have is like now you have like some basic understanding of the key characteristics of reinforcement learning. So you know like, okay, there are some like model based and there are some like model free like reinforcement learning. And for the model based, and there's something called like Markov chain, Markov decision process. And you have a bunch of like probabilities like you can play around with. And remember like the Markov thing is independent of the whole history, so you only care about like what happened in this moment. So yeah, that's all the stuff that I want to talk about today, like for this intro level talk. Oh yeah, and the last thing is there is like a series of courses that I strongly recommend you to take if you are interested in reinforcement learning. Actually, like there are lots of resources online, and I can also recommend like a bunch of resources. But if I give you like a long list here, it may take you like you may like feel confused like which one you should start first. So I will just put like one piece of resource here. So that's the one you need to go into. So that's a course provided by David Silver. So you can just like open the YouTube and then type David Silver. Then you can find a bunch of course classes from him. So he's very awesome. Okay, so that's all the content for today. So thank you so much for listening. So actually, that's my first tech talk after graduation from my PhD. So feel free to connect me on LinkedIn as well. So that's my LinkedIn link. So if you have any thoughts, comments, you want to discuss more, or you want to discuss other topics, like feel free to let me know. And actually, like I don't use reinforcement learning in my daily work, but I use other like machine learning algorithms, like for example, like supervised and unsupervised learning. So yeah, so I mean, I'm very interested to like share more knowledge about those like traditional algorithms. So yeah, if you are interested in that, feel free to reach out to me. So that's all about today. And also like if you have any questions, you can also like just unmute yourself and just ask. Yep.
Awesome. Thank you very much. That was great. Do you have any questions, dear participants? Maybe we can squeeze in a few.
Yeah, I have a question. As far as like getting like initial probabilities for like some of your like that initial Facebook example you gave, like how like difficult is it to get those probabilities? You just look at like historicals for that. Like what would be your process for knowing about that?
Okay, so you mean like the oh yeah, first thank you so much for asking this question, Cal. Are you Cal?
Yeah.
Okay, good. So like you mean like for example in this example, like we got those probabilities here?
Yeah.
Oh yeah, actually those are the parameters of this problem. So you specify those probabilities on your own, but you just need to make sure that the sum of those probabilities like equal to 1. So because like you can go to like Facebook from class 1, go to class 2 from class 1, there's only 2 alternatives here. So that's why like the sum of these probabilities must equal to 1. That's the reason. So those are the parameters. So you give the parameters to this model.
Okay. Yeah, that's a good explanation. That makes sense. Let's say like never mind. That answers my question. I was gonna say like, depending on like the parameters you select, would it make the machine learning algorithm like take longer? I feel like Like if you set like the wrong parameters, it might like mess up time or make it more difficult.
Yeah, I mean, that's a really good question. So actually, like if we just change the numbers in this example, actually we won't change much. But if we change the configuration of this example, for example, if we are in the sleep state, you can see there's no arc going outward. But if you like, I mean, just add another arc, maybe from sleep to class 2, or you just add an arc to itself, just like this arc, and then like the whole setting for this problem gonna change. It may, I mean, it's very likely that it's gonna take longer because like it just like keep doing that again and again here. So there's no like, I mean, like, so that's gonna take longer to solve the problem. However, like you can change like some other parameters as well. Like for example, like in this example, we only have like the class states and we have like the probabilities. But in the Markov reward process and Markov decision process, there are like lots of parameters that you can change. So yeah, I mean, it depends. Like sometimes when you change the parameters, it's gonna make the problem like very hard to solve. That's very possible. And actually, I think there are some like simulation like software online. Like you can like move the parameter a little bit, and you can see the results. And you can search like OpenAI. It's it's like a website. Then there are lots of like simulation examples on that, and you can play with it and to see like how you feel about like playing with these parameters.
Great. Thank you.
Thank you for asking the questions. I think we are just on time. It's 6:30 now. Yeah, I mean, thank you so much for all the participants here, and like feel free to reach out to me like on LinkedIn, like if you want to discuss like anything, or if you want to learn like my experience at Microsoft, not on reinforcement learning. That's totally fun as well.
Awesome. Thank you very much for being so open. Thanks everyone for joining, and stay tuned for the next event.
Thank you, Asana. Thank you, everyone. Bye-bye.
Bye.